Assalamu alaikum. It's our 14th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we are going to solve the perpendicular polarization in electric and magnetic field. Okay, in previous lecture we did the parallel polarization. If you forgot to watch that video, first go through that video first and then move on towards this video for the perpendicular polarization. Okay, whereas the perpendicular polarization concerned in this, now your electric field is perpendicular to the plane. Okay, in previous parallel polarization the magnetic field is perpendicular to the plane, means inward or outward of the page, but in the perpendicular polarization the electric field is perpendicular to the plane. Okay, means inside or outside. Now the components of the wave propagation splits as well as the wave components of the magnetic field splits, while your electric field components is perpendicular to the plane. Okay, now you can see the same. I have two regions, region 1 and region 2, and in region 1 you can also say that like this is your region 1 and this is your region 2. You can say this is your region 1 and this is your region 2. Okay, so in region 1 you can see that there is two waves. This is your incident wave and this is your reflected wave, while in region 2 you can see this is your transmitted wave. Okay, now what you have to do, you can see that, so here you can see this is the direction of the wave propagation, and this is the this is the direction of wave propagation, and this is the direction of the hi, means incident magnetic field. Okay, so magnetic field and the wave propagation component splits into further coordinates, while your electric field is, by using right hand rule you can easily find the direction of the electric field, and the direction of the electric field in the incident scenario is concerned is into the page. Okay, is out of the page. Okay, so for the case of out of, we are denoted by this dot sign, means positive. Okay, you can also calculate the direction of the electric field in this and this in this direction also. Same scenario, this is again out of the page, out of the page. For the case of out of the page, this is in the positive direction and this is denoted by this small dots. Okay, so electric field is perpendicular, while your magnetic field and wave propagation splits into further components, trigonometric components. So this is the basic difference between the parallel polarization and the perpendicular polarization. In previous lecture and parallel polarization, the magnetic field is perpendicular to the plane, but in the case of this perpendicular polarization, the electric field is perpendicular to the plane. Okay, the same scenario, you have to split your coordinates. This is your magnetic field coordinate splitted, and this is your wave propagation splits in the in the region 1. And for the case of region 1, this is the reflected part. Again, this is the HR, means magnetic field in reflected splits into further components, and wave propagation in the reflected part also divides splits. Similarly, for the case of transmitted part, again this is your magnetic field in transmitted and this is your wave propagation in transmitted part. You can split this coordinates by using the coordinates which is given. This is in the z direction. If this, so it becomes z, and if this is the x-axis. Okay, so in this again, the magnetic field, because you know that E and H are tangential components are continuous, so that the magnetic field equations drop on to the tangential lines. Okay, so you know that this is the tangential line, so you can drop. So this is now become in front of theta, there is the vertical component, and this is in the negative x direction, so it becomes minus x sine theta I, and this is the base, and base in the positive z direction, so it becomes z plus z cos theta. Okay, similarly for the case of this is your wave propagation, and wave propagation extends from the normal line, and this is the normal line, so it extends like that. Now it becomes the vertical component, and this is in the positive z direction, it becomes z sine theta, and this is the base which is in the positive x direction, and it becomes plus x cos theta. For the case of always, remember this, incident and transmitted field components are always same, so you can see x cos theta plus z sine theta, x cos theta plus z sine theta. Similarly, z cos theta minus x sine theta, z cos theta minus x sine theta. Okay, keep this. Remember, if you have shortened time, you can direct use these values. Okay, incident and transmitted field equation solution is same. Okay, while your reflection is somehow different, so you can easily find by the same concept. This is in the negative z direction and this is base, so it becomes minus z cos theta. This is in the negative x direction and this is the vertical component, so it becomes minus x sine theta. Similarly, for as this concern, for the case of wave propagation components, this is in the positive z direction and this is the vertical component, so that's why this is that sine theta. And this is the horizontal component base and this is in the negative x direction, so it is x cos of theta. Now what you have to do, you have to write the field equations of these region 1 and region 2. So let's start by writing the field equations. Now these are the field equations in region 1 and region 2. Okay, in region 1 you know that there is incident plus as well as the reflected part for the, and you know that uh, the plane is x direction and the plane is in the z direction, because your electric field is perpendicular to the plane in perpendicular polarization. So that's why for the case of electric field, the direction is always in the y direction, but either positive y or negative y, you can find it by right hand rule. Okay, you can easily find. For as in this scenario is concerned, uh, when your magnetic field in this and your wave propagation is in this direction, so your electric field direction is uh, out of the page. For the case of out of the page, we are using positive, so that's why it becomes positive y. For the case of incident, the amplitude is e naught I, and again in perpendicular polarization, as I told you, the component which is perpendicular has been not subdivide into other components. In this perpendicular polarization, the electric field is perpendicular, so that's why the uh, coordinate components of the electric field is not subdivided, so that's why only y direction for the case of electric field, and e naught I is the amplitude. Now exponential e power iota k1, because you are in the first region, definitely the wave propagation is split into two, which is the x cos theta and z sin theta. So you can see x sin theta, sorry, z sin theta plus x cos of theta I minus iota omega d as it is. Similarly, for the case of reflection, again your magnetic electric field in the y direction, by using right hand rule, you can see this is in the positive y direction. So positive y e naught r, because electric field not splits in further components in the case of perpendicular polarization, but it splits in the case of parallel polarization. Okay, so the amplitude is now e naught r, and the again the exponential term e power iota k1 as it is, and definitely the wave propagation parts is divided into z sin theta minus x cos theta, z sin theta minus x cos theta minus iota omega t as it is. Similarly, for the case of magnetic field in region 1 and 2, in region 1, sorry, in region 1 is the sum of incident plus reflected. So definitely the magnetic field components is divided into two components, which is z cos theta I minus x sin theta I. So you can see z cos theta I minus x sin theta I, whereas the amplitude can be written as e naught I divided by z1, because you know that h basically equals to e by z. For the case of incident, it becomes e naught I divided by z1. Okay, similarly e power iota k1 as it is, and the components of the wave propagation is this. You know that x cos theta plus z sin theta, you can write minus iota omega t as it is. Similarly, for the magnetic field, for the reflected part is this, and its amplitude can be denoted at e naught r divided by z1. Okay, and yes, the components of magnetic field is subdivided, which is minus x sin theta minus z cos theta minus z cos theta minus x sin theta e power minus iota k1 as it is, and the components of the wave propagation, which is this z sin theta minus x cos theta, z sin theta minus x cos theta minus iota omega 3 as it is. Okay, so this is how you can write the field equations of electric field and magnetic field in region 1, while you can see in region 2 there is only transmitted part. Okay, this is only transmitted part, and the electric field is subdivided. You can see that the electric field is sub again is the electric field is the perpendicular component in perpendicular polarization, so that's why only the direction is in the positive y direction. In E naught t is the amplitude, whereas the wave propagation concerned e power iota k2 y k2, because now you are in the second region. Okay, your wave propagation splits into further components, so z cos theta minus x sin theta. Sorry, this is the magnetic field, this is the components of the wave propagation, x cos theta plus z sin theta. Okay, x cos theta plus z sin theta minus your omega 3 t as it is. While your magnetic field is concerned, magnetic field definitely splits into two component, which is z cos theta minus x sin theta, z cos theta minus x sin theta e power iota k2, because you are in the second medium, and exponential power the terms of the wave propagation, which is this x cos theta plus z sin theta, x cos theta plus z sin theta e power minus your omega t as it is. So this is how you can write the field equations in perpendicular polarization. Okay, now what you have to do, you have to apply the boundary condition. As you know that this is your normal line, because normal line is always between the incident and the reflected part. The incident and the reflected part in between line is always the normal line, and the other line must be the tangential line. So you have to apply the boundary condition with the tangential, with the normal line. So in normal there is x, so you have to apply the boundary condition at x equals to 0. Now where there is x, you have to put it equals to 0, and then you have to rewrite those equations. So let's start. So here is the boundary condition at x equals to 0. You just have to put the value at x equals to 0. Here you can see here is x, so this part becomes 0, and here is x, its part becomes equals to 0. And e power minus iota omega t and e power minus omega t take common, and here also e power minus iota omega t, e power minus iota omega t cancels with this, and this is y direction a, and here is also y direction, so take common y direction from here, cancels with this y direction, because you know that at boundary condition at x is equals to 0, your tangential components of electric field and the magnetic field is are tangential components of E, and tangential components of H are continuous. So you have to do E equals to this. Okay, means that this equals to this, means E1 t equals to E2 t, and E1 t there is two terms, this it must be equals to this. So you have to do this by putting the bounding condition at equals to x equals to 0. Whenever there is x, you have to put 0. Okay, so you will only left with E naught I and the exponential term e power iota k1, and only left with z sine theta I, because other term with x it becomes 0, and also plus e naught r e power iota k1 z sine theta r. Okay, and this becomes 0 and this cancels, so equals to e naught t e power iota k2 z sine theta t. Okay, because x term becomes 0 and this iota omega t cancels with taking common from this. Okay, so this, now what you have to do, you have to apply the Snell's law. You know that Snell's law basically theta I equals to theta r, in which k1 sine theta becomes equals to k2 sine theta. Okay, so putting that, so exponential terms after k1 sine theta becomes equal to k2 sine theta, so the exponential term of this becomes equals, take common from this, cancels with this, you will only left with e naught I plus e naught r equals to e naught t. So this is your first equation. Similarly, you have to apply the second bounding condition, which is h1t equals to h2t, means you have to equal this equation with this by applying the bounding condition at equals to 0, putting x equals to 0, this becomes 0, and this becomes 0, and this x term becomes 0. Okay, okay, so you will again e power minus iota omega t common, you can take common, and you can easily cancel taking common, and e power minus iota omega t cancels with this. Here is also you can see here is z1, here is z1, it goes to the other side, becomes z2 by z1. So let's start. So it becomes, this becomes 0, so you will only left with e naught I divided by z1. You can see e naught I divided by z1 and z cos theta I, z cos theta I, and the in exponential this becomes 0, and you will only left with e power iota k1 z sin theta I. Okay, z sin theta I. Similarly for the case of this, here e naught r divided by z1 minus e, because there is minus with z cos theta, because x term 0, you will only left with minus z e naught r divided by z1 cos theta r, and in exponential again x becomes 0, you will only left e power iota k1 z sin theta. Okay, Similarly, for the case of transmitted part, it becomes E naught t divided by z2, E naught t divided by z2, and z cos theta t, z cos theta t, because x becomes 0 because boundary condition is x equals to 0, and in exponential again this becomes 0. You will not be left with this direction. Again you have to apply the Snell's law here. Okay, after applying the Snell's law, exponential term this becomes equals to this, becomes equals to this, because all exponential terms now equal after applying Snell's law. So taking common exponential term from this cancels with this, you will only left with this and move, taking common in denominator z1 from this and multiply to the other side, it becomes z1 by z2 to the other side. So final relation equation 2 now becomes e naught I cos theta 1 plus minus E naught R cos theta 1 equals to E naught I, Z1 by Z2 E naught T cos theta 2. Why this theta I becomes cos theta 1 and theta R becomes theta 1? Because you are in the first region, and we know that when we apply Snell's law, incident must be equals to reflected. So incident equals to reflected we take as 1. So that's why incident angle and reflected angle both equals to theta 1, while the transmitted angle equal to theta 2. Now what you have to do, our task is to find the reflection and the transmission coefficient. How we can find? We can find that by just from equation 2. First of all, we have from equation 2 we have to find the value of E naught t. After finding the value of E naught t from equation 2, we have to put that value in equation 1. So from equation 2, E naught t, z2 divided by z1 multiplies to the other side, becomes z2 by z1, and this is as it is, and other side divide by cos of theta 2. So E naught t becomes equals to this. Now what you have to do, you have to put this value of E naught t in equation 1. This is your equation 1. So E naught I is as it is plus E naught R is as it is equals to E naught t, which you already find this value. You have to write it as here. Now what you have to do, you have to multiply inside. So z2 divided by z1 multiplied by E naught I cos theta 1 divided by cos theta 2 minus z2 by z1 E naught R divided by divided by cos theta 2 multiplied by cos theta 1. Okay, now what you have to do, you have to just move incident terms on one side and the reflected terms onto the other side. So you can see here, this is the reflected part. I move this to reflected part, reflected and reflected, and this E naught I move to the other side, it becomes minus E naught I, and here already incident terms, so incident, reflected, reflected. Okay, so this. Now let's further proceed, because we have to find the reflection coefficient. So we, what we have to do, we have to take common E naught R from this, and taking LCM, and we have to take E naught I common from this and take LCM, and we have to divide E naught R divided by E naught I, and it becomes like this. So in denominator they cancel, so you will only left with E naught R divided by E naught I, which is equals to z2 cos theta 1 minus z1 cos theta 2 divided by z2 cos theta 1 plus z1 cos theta 2. This is the reflection coefficient. So how you can find the transmission coefficient? You just have to divide your equation 1 by E naught I. This is your equation 1, just divided by E naught I. So it becomes 1 plus E naught R divided by E naught I equals to E naught T divided by E naught I. E naught R divided by E naught I we already find. You have to put this, taking LCM, this cancels with this, and this z2 cos theta 1 plus z2 cos theta 1, it becomes 2 z2 cos theta 1 divided by z1 cos theta 2 plus z2 cos theta 1. This is your transmission coefficient. Okay, so that's all for this lecture number 14, how you can find the transmission as well as the reflection coefficient, okay, in the case of perpendicular polarization. So the key concept is only that in perpendicular polarization, you know that the electric field is perpendicular to the plane. Okay, if x and z are the planes, then definitely the electric field is must be in the y direction, because in perpendicular polarization the electric field must be perpendicular to the plane. Okay, while in parallel polarization, which we did in lecture number 13, the magnetic field is must be perpendicular to the plane. Okay, If you forgot that video, you can watch that video first, then you can watch this video. Okay, so this is the only difference between the perpendicular and the parallel polarization. And you can also see the results for the case of parallel polarization in the case of reflection and transmission coefficient, that the components are similar, z1 and there is theta 1, z2 theta 2, okay, similar parts. While in perpendicular coordinates you can see there is opposition, whereas z2 there is theta 1, whereas z1 there is theta 2. So that's all basically the difference between the parallel and the perpendicular polarization. So that's all for this lecture number 14 for perpendicular polarization of advanced electromagnetic field and waves. So thanks for watching. Till then, Allah Hafiz.